and Physics, Universitas Pembangunan Nasional, Veteran Jawa Timur. Today we will discuss unit chapter about multi-domain system modeling. Let's start this.
Okay, let's start with why. Why we study multi-domain systems. In many classical engineering and physics courses, we study system in isolation. Mechanical system are discussed in one course, electrical circuit in another, and thermal processes in somewhere else. This approach is useful for building foundational knowledge, but it doesn't reflect how real systems actually operate. In practice, most engineering systems are multi-domain in nature. A clear example is an electrical motor. Electrically, it draws a current and consumes power. Mechanically, it produces torque and rotational motion. At the same time, part of the energy is converted into heat due to losses. These domains, electrical, mechanical, and thermal, are all interacting simultaneously. If we analyze only one domain and ignore the other, our model will be incomplete and potentially misleading. That is why multi-domain system modeling is essential. It allows us to represent energy transfer and interaction consistently, enabling more accurate prediction of system behavior, performance, and efficiency. Okay, if we look at the slide, we have other example such as in insulin pump or the dialysis machine. This machine combining electrical, mechanical, and fluid system. And then we have a robot system. And then we have robotics and automation system. The system integrate mechanical movement, electrical control, and often thermal consideration. So this course will provide the tools to accurately model and predict the behavior of such integrated system. Let us consider a real-world example, an electrical vehicle. In this system, multiple physical domains are inherently interconnected. Electrical energy from the battery is delivered to the power electronics and motor, which convert it into mechanical energy to drive the wheel. Meanwhile, thermal energy is generated from electrical and mechanical losses, requiring careful management to avoid overheating and performance degradation. If we model only the electrical subsystem, we ignore mechanical and thermal effect. If we focus solely on mechanical motion, we miss electrical constraint and losses. Such isolated analysis cannot capture the true system behavior. Multi-domain system modeling overcomes this limitation by integrating all relevant energy domains into a single framework, providing a comprehensive understanding essential for designing reliable and efficient real-world system. So, what is multi-domain system modeling? In simple terms, multi-domain system modeling is the art and science of representing systems that involve more than one energy domain within a unified mathematical framework. The key idea here is unified mathematical representation. Instead of developing separate equation for electrical system, mechanical system, and thermal system, we aim to describe the entire system using a single, consistent set of equations, independent of the physical domain involved. Another important principle is the emphasis on energy exchange. In a real system, energy is not only stored but also transferred and dissipated across different domains. Understanding how energy flow and transform is central to accurate modeling. Finally, power flow analysis allows us to examine how power moves between coupled domains. This will help in identifying critical interface and potential bottleneck. Overall, this approach enables engineers to analyze and optimize complex systems at the system level rather than treating each domain in isolation. Before we combine multiple physical domains, it is important to revisit what we already know about single-domain dynamic systems. These systems form the foundation of all multi-domain modeling. In mechanical systems, we commonly use mass spring damper model governed by Newton's law. These models describe how force produces motion through inertia, stiffness, and damping. In electrical system, dynamics are described using Kirchhoff's law, leading to familiar RLC circuits models involving resistor, inductor, and capacitor. Fluid systems are typically modeled using conservation of mass and momentum, such as fluid tanks, pipes, and flow resistance. Similarly, thermal systems are governed by the conservation of energy, where thermal capacitance, conduction, and convection determine temperature dynamic. Each of these systems already follows a well-defined dynamic law. The key idea in multi-domain modeling is that we do not redefine these laws. Instead, we connect this existing model through energy exchange and power flow, allowing us to analyze complex systems as an integrated whole rather than as isolated component. This slide summarizes the concept of energy domain in engineering systems. In any physical domain, power transfer is defined by a pair of variables, an effort variable and a flow variable. The product of these two quantities represent power. In mechanical translation system, the effort variable is force and the flow variable is velocity. For rotational mechanical systems, torque and angular velocity play the same role. In electrical systems, power is transferred through voltage as the effort variable and the current as the flow variable. Fluid systems such as hydraulic and pneumatic system use pressure and volumetric flow rate to describe energy transfer. In a thermal system, the effort variable is the temperature difference, while the flow variable is the heat flow rate. Recognizing these effort flow pairs is essential because it allows us to describe different physical domains using a unified framework. Once these pairs are identified, systems from different domains can be interconnected consistently without changing their fundamental physical law. This slide presents the unifying concept of effort and flow variable, which is central to multi-domain system modeling. Across all physical domains, energy transfer can be described using these two variables. Effort variable represents a generalized force or potential that drive a process, such as force in mechanical system, voltage in electrical system, pressure in fluid system, and temperature difference in thermal system. Flow variable represent the corresponding rate of transfer, including velocity, current, volumetric flow rate, and heat flow. The key principle is that the power is always equal to effort multiplied by flow. This universal relationship allows us to describe energy exchange consistently. Once systems are expressed in effort flow form, they can be treated uniformly, regardless of their physical nature. This is what enables multi-domain systems to be modeled and interconnected within a single framework. This slide highlights the use of analogies between domains, which is a powerful tool in multi-domain system modeling, because the governing equation across different physical domains often share similar mathematical structure. We can map a component from one domain to another. For example, in mechanical system, mass representing inertia, which analogous to inductance in electrical system. Mechanical damping behave like electrical resistance, and spring correspond to electrical capacitance. These mapping are known as force voltage analogies, although other analogies such as force current or thermal electrical analogies are also commonly used. By using these analogies, engineer can apply a familiar modeling technique from one domain to another. This creates a shared language across discipline, simplifying analysis, improving communication, and enabling more efficient system-level modeling. Analogies are not merely conceptual aids, they play a practical and important role in modeling, analysis, and simulation. By recognizing that different physical domains share similar mathematical structure, we can transfer established technique from one domain to another. For instance, a method originally developed for analyzing electrical circuit, such as a network equation, impedance, and simulation tool, can be indirectly applied to mechanical, fluid, or thermal system through appropriate analogies. This allows engineers to reuse a proven modeling approach rather than developing a new method from scratch. As a result, analogies significantly reduce learning barrier, especially when working across disciplines. They also improve the design efficiency by enabling faster system-level analysis and more efficient collaboration between engineers from different fields. There are several strategies available for modeling dynamic system. The most fundamental approach is the use of differential equation, which directly describe system behavior based on physical laws. While powerful, this method can quickly become complex as system size and coupling increase. Space modeling provides a more compact and systematic representation. It is particularly well suited for control analysis and design, as it organizes system dynamic into a structured set of first-order equations. In contrast, energy-based and graph-based method emphasize system structure and power flow rather than individual equation. These approaches are especially effective for large multi-domain systems, where understanding energy exchange and interconnection is critical. They offer scalability and clarity that traditional method often lacks. And this slide shows a classic multi-domain system, a DC motor. An applied electrical voltage drives the current in the winding, which generates torque and produces mechanical rotation. At the same time, the rotor's motion induces a back electromotive force that opposes the applied voltage and affects the current. This creates a bidirectional coupling between electrical and mechanical domains. Because these interactions occur simultaneously, both domains must be modeled together. Ignoring either side leads to inaccurate prediction of motor behavior and system performance. This slide presents the mathematical model that bridges the electrical and mechanical domains of a DC motor. On the electrical side, Kirchhoff voltage law relates the applied voltage to armature resistance, inductance, and the back electromotive force. On the mechanical side, Newton's second law for rotation governs the motor dynamic, accounting for inertia, damping, and generated torque. The key connection between these domains lies in the torque constants and the back EMF constant. Together, this coupling terms unify both equations into single dynamic system that accurately represent electromechanical behavior. Simulation is a crucial step in multi-domain system modeling because it allows us to study system behavior before building physical prototypes. By simulating a system, we can observe transient responses, steady state behavior, and overall stability. Time domain analysis help us to evaluate key performance metrics such as rise time, overshoot, and settling time. In addition, parameter sensitivity studies allowed us to understand how changes in variables such as motor inertia or electrical resistance affect system performance. These insights are essential for efficient design optimization and risk reduction. Modern software tools make multi-domain modeling practical and efficient. Simscape allows engineers to build models using physical components across multiple energy domains. Modelica takes a different approach, using equation-based and domain-independent modeling, which is well suited for complex systems. Multiphysics tools such as COMSOL extend this further by capturing spatial and field effects. The choice of tool ultimately depends on the system complexity and the system modeling objective. Multi-domain system modeling reflects how real engineering systems actually operate through the interaction of multiple physical domains. By adopting an energy-based perspective, we gain a unified framework that allows mechanical, electrical, thermal, and fluid systems to be treated consistently. Modeling approaches such as a state space representation and bone graph help manage the complexity while preserving physical insight. Mastery of multi-domain modeling enables engineers to design, analyze, and optimize systems at the system level rather than isolated components, leading to more robust and reliable design. To close this chapter, consider everyday systems such as air conditioner or smartphone. Although they appear simple to the user, these systems are built from multiple interacting domains. Electrical circuits provide power and control. Mechanical components enable motion or airflow. Thermal processes govern heating and cooling. In some cases, fluid systems play a critical role. All of these domains work together to achieve a single integrated function. Recognizing and identifying this interaction is the first and the most essential step toward effective system modeling and meaningful engineering analysis. In conclusion, I hope this lecture has provided a clear and useful understanding of the fundamental principle and analytical tool of multi-domain system modeling for the analysis and design of complex system engineering. Thank you very much for your attention.